So that is the main essence of adding question 8 and 9. Alright? But for question 10 to 15, we'll look at what we call the basic idea based on the solubility expressions, together coupled up with some questions from the acid and base equilibrium. Okay. So now, what do we need to know? We are told at 327 degrees Celsius, the equilibrium concentrations of a certain reaction were given. And the reaction that we had, basically we had that. Okay, of course, whenever we're talking about equilibrium, we talk about reversible reactions, so something that we can express in such a form. Is that visible enough? So now we are told at equilibrium the concentrations are as follows. For this reactant, we've been told is 0.15 molar concentration. For the products carbon monoxide, it's 0.15. Then for the hydrogen gas, 1.1. I'm sure we are very much aware that whenever we are finding our Kc, we basically get to look at the equilibrium concentrations, right? So in a case where we've given you the initial concentrations before chemical equilibrium, you get to first of all use what we call the ice table to find the equilibrium concentrations. But in such a question, in this question, we've already been given the equilibrium concentration. So now what is the question asking us to find? The question says calculate Kp at this temperature. Strange, Kp and not Kc. So we use the concentrations to find Kc. So we said our Kc basically is equivalent to us to what? To Kp. Our Kp is basically equivalent to Kc multiplied by what? What did you say? Is it the other way around? Which one is which? Kp is equal to Kc multiplied by RT, the power what? Okay. So if we can find Kc, do we know what our value of R is? 0. What? What's a gas constant? 0. What? 0.08 something. Okay. So what is the change in N there? You look at the change in number of moles, of course. So first of all, our Kc is going to be given as what? We said products, in this case we have carbon monoxide and what? And hydrogen gas. So not only did we say you multiply them, you said you're supposed to be raised to what? What did we say? What are the powers for carbon monoxide and the hydrogen gas? Then for the reactant, which is on the bottom, so we said you need to look at the stoichiometric coefficients in the equation, right? That's what we said. So now in this case we now have everything. Our carbon monoxide will substitute there. We have 0.15. Our hydrogen is 1.1. 1.1 squared divided by our reactant, which is 0.15. So grab your calculator there. I'm sure there is no need for us to use a calculator there for the first part. We can clearly see that the concentration of carbon monoxide and the reactant were basically one and the same, and they can divide. So then 1.1 squared is going to give us what? So I'm getting 1.21 as our Kc. Any questions there? Do we have questions? So what is the revision? We've revised how to determine the Kc. So how do we get to find the Kp now? So our Kp is therefore going to be, our Kc is 1.21. What is the gas constant there? Not this value. 0.8206. Okay, or 821. That's so it's this value that we're talking about, which comes with Kelvin. 0.0821. Okay. So 0.0821. Our temperature is supposed to be in Kelvin because the units for this value of R comes with Kelvin. So we've been given 327. How do we move from degrees Celsius to Kelvin? So you need to add by what? You need to add what? 273, right? So we're going to have 600 kelvins. The power. Now change in number of moles. How do we get to determine that? So we said look at the number of moles of what? Of the products. So add their stoichiometric coefficients. 1 plus 2 is going to give us what? A 3, right? Minus a 1 on the left for the reactant that we have. We're going to have how many moles? 2, right? Any questions there? Any questions, guys? Okay. So there are no questions. So the value of Kp, I'm getting 2936.1. Any questions? So I want you guys to be part of the calculations, part of the solving, part of the talking, part of the contributions, so that we get to move together. I don't like talking a lot for over an hour alone. I don't enjoy it. Are we okay? So we've answered question 8. Question 9. At 25 degrees Celsius, our K value has been given to be 0.090. The equation that we had water plus that. But for the people who watched the video, I'm sure you saw that I answered these questions already, right? Question 8 and 9 were already answered in the video. Gideon, I'm sure you watched the video, not so? Okay. So calculate the concentrations of both species at equilibrium for each of the following cases. So we've been given the mass. Okay. So we've been told 1.01 gram of that, 2.0 gram of that. They are mixed in 1 liter of a flask. So now the question is, calculate their concentrations. So a value of K is given, right? So we do understand that our value of K is basically dependent on the equilibrium concentrations, right? So in this case, our products, we just have 1 raised to that power 2 over what reactants do you have? We had water and C2O. So these are going to be raised to power 1 because we just have stoichiometric coefficients of 1 there. So now, remember, our goal is to get to find the concentrations at equilibrium. Okay, that is our goal. So now, this is the formula of our K. So if we can substitute the equilibrium concentrations of all these reactants and products in terms of our variable X, it is going to be easier for us to get to simplify and be able to determine what? Determine the value of x, then we'll be able to find everything. So let me get to look at that. So now, why do you think we've been given the masses? Because if we go back to our ice table, we need to show these: the initial concentration, the change, and also the equilibrium concentration. So why have we been given the masses? Why do you think we've been given the masses? For what purpose? What purpose are they serving? Because we need to have the initial concentration there, then the change and the equilibrium. So for us to be able to find the equilibrium concentration. So how do you get to find the initial concentrations? So I'm sure you guys do understand that the concentration is given as the number of moles dissolved in what? In a volume of a solution. Not so. So why have we been given the mass? For what purpose? We've not been given the concentrations. Yes, sorry guys. That's a very simple question. You're quiet? So if we can find the moles given this volume, we're able to find the concentration, right? Not so. So now, if you look at water, what is approximately, I believe the molar mass of water is approximately 18.016 grams per mole, right? So we can use the mass there. We know that number of moles is basically mass divided by the molar mass. So 1 divided by 18.016. So we have an initial concentration of water to be 0.056 molar concentration. Then for the other reactants, chlorine, if you check the periodic table, what are you going to see as a molar mass of chlorine on the periodic table? It's what? I've forgotten. Is it 35.5? Anyone with a periodic table? No, okay. I have not forgotten. So 2 multiplied by 35.5, then oxygen is 15.994, if I'm not mistaken, 994, something like that. So what are we going to have as a molar mass for that reactant? So we don't have calculators. I'm sure you've been taught by physics tutor that always have calculators whenever you have a class. Is that the molar mass that you get to? So for us to find the concentration, we need first of all to determine the number of moles, right? So a number of moles, divide that into the 2. So I have 0.023. So I'm saying molar concentration because if I divide by the given volume, which is a liter, nothing is going to change about it, right? It's still going to be the same. So that is our concentration. In a case where we have a different volume, like in the second part of the question, you need to divide by the 2, which is going to change the value that we have. Are we together there? Am I talking to myself? So if you look at the question that we've been told calculate the concentration of all species at equilibrium for each of the following cases. 1 gram of water and 2 gram of fat are mixed. So meaning that at the start of the experiment you only had water and this other reactant. The product was not available, so you can put 0 molar concentration there initially. And I don't necessarily mean that every time initially you are going to have a 0. No, you need to understand the question. In some cases you start a reaction while you already have part of the products in the solution. So you need to understand when to do what and what to write under your initial concentrations on the products part. Okay, so now the change basically is based on the stoichiometric coefficient, and it depends on what you're talking about. If you're talking about the reactants, we put a negative to indicate that there's a loss or a decrease. So for water we're going to put a minus x. For this other part we're going to put a positive 2x. So 2 is coming from the stoichiometric coefficient. So if we had the 2 there, it would have been minus 2x there. The negative is showing that it is a reactant that is supposed to reduce as the reaction gets to progress. So the equilibrium concentration is supposed to be the initial plus the change. So we have 0.056 minus x, 0.023 minus x, and 2x there plus 0 is just 2x. So we now have the equilibrium concentrations that we needed or required. So what can we do at this stage? We do know that basically the K is dependent on this equilibrium concentration. So our K is given to be 0.090. Then we said you need to multiply the products. So for our product we only have 1, which has got 2x there. So we said it's supposed to be raised to a stoichiometric coefficient, which is a 2. So the power 2 over what our reactants in this case, we have that and this. They are all going to be raised to the power 1 because they have stoichiometric coefficients of 1. So we have 0.056 minus x multiplied by 0.023 minus x. So you can clearly see that we can come up with a very complicated quadratic function here for your own information. Okay. So now there is something that we get to do to simplify our work. So we get to cancel out anything to be added or subtracted. And basically if you get to find the value of x, you are going to see that even after substituting in this on the right hand side, you are still going to have a value closer to that. So this minus or the plus, it may be plus, they don't basically have an effect on the value of our answer, especially in a case where we have low values of our K. They only get to have an effect if you have bigger values, like maybe for example they say your K is equal to 10. In such a case, just go by the quadratic and get to simplify. But in a case where these are less than 1, it's very much okay for you to cancel out the addition and the subtractions, so that you just get to simplify it directly. So that you remain with this multiplied by that 0.056 multiplied by 0.023, then multiply by 0.09 since we're crossing and multiplying there. So I have 0.0011592. Then this side 2x squared is 4x to the power 2. Divide by 4, then find the root on the other side. So the value that I'm getting for x is 0.005383. Okay, in terms of such standards or scientific notation, the value that we are looking at is what? 5.38 times 10 to the power negative 3. That is our value of x. So now you need to go back to what we had as our equilibrium expression as well. So can you remember what we had? For the first part, for water, what was our equilibrium concentration? We said 0. What? Is it 0.023 minus x? Then this one 0.0 what? Am I okay there? I can't remember what we had. Okay, so this was minus x, then the other part we had 2x, right? So all you get to do is now plug in the value of x that you found. Okay, and the value of x that you found is what? 5.38 times 10 to the power negative 3. So for you to find the equilibrium concentration, substitute in this part, that part, and that part. Any questions? But I'm sure, guys, is there any possibility of you guys failing a question under chemical equilibrium? I doubt, because I think we have 2 videos on that, plus the lessons that we've been having. I'm sure you're okay now. These are free topics. Free marks. Are we okay? Are we okay? Or we're doubting if we're okay? Okay, the second part of the question is very interesting. It says we have one more. So in this case, we've been given the products. So this is now placed in. It's placed in a 2-liter container. That's what we have. You have one more of that, and then you place it in 2 liters, in a 2-liter flask. What do you need to do there? So as you get to come up with your ice table, in this case, this is a reversible reaction. So you can consider the other side now to be the to be the reactant side. Okay, that's very, very important for you to understand that. So you have 2 options, but I wouldn't want to complicate your lives or your work. It's either you can say 1 over k. You consider this, or you write the equation remain as it is, so that you can have then get to exchange the what. So then maintain the right hand side as it's supposed to be. But I think it's easier to think of it in this way, where you make 2 HOCl this side, then these other ones now consider them to be your products. Okay. Yeah, that is better. But all the same, your value of k is going to be 1 over k. Okay. Because that was given for the forward reaction as it is written. So if we are going to reverse the reaction, the value, I'm sure you did watch a video where I was solving your tutorial sheet. So it's basically 1 over k if you reverse a reaction. Okay. So the other side remains the same. For our products, we have water and C2O over what? Over HOCl, which is acting as a reactant in this case. Okay. So now the question is, we have 1 more of that in a 2 liter. So what do we have? We have this concentration, right? So you have the initial concentration of this reactant, which is given to be what? So 1 more in 2 liter. What is the concentration? 1 divided by 2 is going to give us what? You have 0.5, right? Not so. So for the reactant, you're going to have 0.5. So we didn't have anything of the products. The change here minus 2x, positive x. So you have 0.5 minus 2, positive x. So as you get to plug in there, you're going to see that you're going to have 1 over the given value of the constant to be 0.09 equal to, on top, x times x is going to be x squared. Denominator part, you have this squared. So 0.5 minus 2x the power 2. So equally there, you get to do the same, cancel out the minus 2x and focus on the 0.5. Is there any challenges when it comes to simplifying what I've come up with? We have 1 over 0.09 being equal to x squared over 0.5 minus x the power, or minus 2x. So we remove this part. Then you have 0.5 squared, which is going to be 0.25. Multiplied by 1, x squared multiplied by 0.009, and then you get to find the value of x. Then you get to go back to this, plug in here to find the equilibrium concentration. The value of x will still be the equilibrium concentrations of the other two products, water and the other reactants. Okay, I'll allow questions. Are we together? People have already left. People are very impatient. Okay. Let's try to talk about this new thing now. That was just like a recap of what you guys already covered. So we built product expressions. So this is a component that we get to talk about the issue of determining how soluble something is. Of course, we look at solubility in this case as in terms of the concentration. So when you're coming up with determining the solubility of a KSP value, which tells you how much something is soluble in a given solution, you need to look at what we call dissociation reactions. So for example, if you have aluminium OH3 there, this is so this is an example of a solid that you can have. So you have aluminium, then you have hydroxide. So now this is an example of a solid that you can have. Okay. So you have a solid. So you need to write what we call the dissociation reaction, which will show the way it's going to break down into its ions. So you can basically see that you had aluminium 3, right? Reacting with 3 hydroxide ions. So you may say, where is the 3 positive coming from? I'm looking at that 3 because when you're coming up with a formula, you need to exchange these guys so that you have aluminium 1 and then hydroxide 3 there. Are we set there? Are we set? So now, how do you get to come up with a KSP expression? The KSP expression, so repeat product constant, it is dependent on what? So this is in solid form, the ions are in aqueous states, right? And there's one point that I made. I said when you're finding the K, it is only dependent on what? On what states? Aqueous and what? So solids and liquids are not part of the K expressions. It may be KSP, it may be KP, it may be KC, it may be KB, it may be KA. Okay, depending on that, on what kind of equilibrium you're talking about. So in all those cases, we ignore the solids and the liquids. So in this case, therefore, we're just going to have aluminium 3 plus being multiplied by the hydroxide. So these are supposed to be raised to their stoichiometric powers, right? So 3 and 1. So the solubility of the ions is basically going to be one and the same. So we get to put X to denote them. So in the brackets, I'll put X and then I'll put X as well. So now the question is, where is the mistake? Who has noticed the mistake that I've made? I'm trying to come up with a value of KSP directory without coming up with an ICE table. Okay. So this was supposed to come the way it is, 3x. So now where is that coming from? If you go back to your ICE table, you're going to see that solids don't appear. So you have initially you have 0, then you have 0. For your change, you are going to have positive x for both. Sorry, you're going to have, but you are going to go by the stoichiometric coefficient. So you're going to have x and 3x for your change. Then for your equilibrium, you're going to have the same. Why is it remaining the same? Because at the start, you only have solid. You don't have the ions. So this one, there's no need of you even coming up with an ICE table. It's just a matter of you understanding that. Go by what you have. So here you have x, there you have 3x. Then they're supposed to be raised to their stoichiometric power. So you have x multiplied by 27x to the power 3, which is 27x to the power 4. So if I give you x, in this case denotes what? We've said this is the KSP. Now x on the other side denotes what? It denotes the concentration, which we are calling what? The solubility. Are we together? Let's get to look at another solid dissociating. What if we talked about calcium phosphate? And what do we expect to have there as our products? So we're going to have, how many calcium ions do we have? There are 3, right? With a charge of a 2. Then phosphate ions, there are 2 as well, with of course a power of a 3 minus. Okay. Any challenges with coming up with splitting? I'm sure splitting there are no challenges, right? You just need to look at what you have. Moreover, it doesn't even matter the charge. Okay. But anyway, it's important that you understand how the charges are coming about. So in this case, our KSP is going to be what? We have 3 there, right? So we have 3x, the power what? The same power 3. Then the other one we have 2, so we'll put 2x, the power 2. So we have 27x to the power 3. Then you have 4x squared. Because 3 to the power 3 is 27, x to the power 3 is 3, 2 to the power 2 is 4. Okay. 27 times 2 is 54. 54 times 2 is what? 108. Let me try. So 108 x to the power 5. So given the solubility of the concentration, you're able to find the KSP value of a solid calcium phosphate. Okay. I have a backache now. Go to question 11 from the document that I sent you. Question 11. Are we there? So we have, are we there, guys? Yeah, so that is our dissociation reaction that we have. How do you get to look at it? Some of these things you need to write something that is making sense, okay? So does this make sense? Remember, calcium has got a 2 plus, right? So how can we write this better? It's calcium CO2, 2, right? Does that make sense? Because we know calcium comes from group 2, so it has got a charge of 2. So this one has to have a 2. So that we can see that basically it was basically carbon dioxide. They just wanted to confuse us. Yeah. Are we okay? It's like you guys now understand fast. Don't have questions anymore. So we have calcium 2 plus 2 carbon dioxide molecules. Of course, that may be in gaseous. This is in aqueous. So all those appear in the KSP expression. So we have 1 calcium, so X. Then for the carbon dioxide, you have 2 of them, the power 2. So I have X multiplied by 4 X squared. Then you have 4 X to the power 3 as our KSP expression. So now in this question, they've even given us the solubility. We've been told the solubility for that solid was 4.8 by 10 to the power negative 5. So now where there's X, you get to put that. The power 3. Then multiply by 4. So 4.8 by 10 to the power negative 5. Rest the power, just the third power. Multiply by 4. So the value that I'm getting is 4.42 times 10 to the power negative 13. What units are we going to have for our KSP? Do we have any units for a constant? So, any questions? Or now we've done our calculations. Do we have questions? Okay, so question 11 remains the same. The last question that I want us to look at is question 12. For one reason only. Because this is a case where they tell you to find the KSP. In a case where they've told you the KSP for... No. Okay, they've given us a KSP already. And then they're asking us to find the solubility of silver sulfate. In a case where you have water and all those ions in the solutions. A very good question. I'll answer the first and the second part, then I'll leave the third part for you guys to just get to look at what you're saying. So our KSP value of this solid that we're calling silver sulfate is 1.2 by 10 to the power negative 5. That is our value of the KSP there. We need to calculate the solubility of silver sulfate in each of the following. Okay. So the solubility, one, in a case where you have water. The other part, in a case where you have 0.10 molar concentration of what? Of the Ag silver nitrate. So what I want you guys to understand is basically the same concept of the ice table applies to even the solubility expressions. So if you want to get your marks, make sure you think of it in such a way. so that you get to have your Ag2 there, SO4. It's going to split to what? So we have 2 silver ions and sulfates. Okay, so we said we don't show what? The solids. We're not interested in them. So for our initial, in case where we are putting this solid in water, is there any initial concentration in water of any of the ions that we are talking about? There is nothing, right? I want to hear a response on that one. Do you have any ions present in water that we are talking about in this solid of the discussion here? Silver and sulfates. Are any of these present in water? Excuse me. So they are not, since you don't want to respond. So there is nothing there. So in short, basically, the KSP just goes as it's supposed to be. So we have 2x, we have x there, then we have 2x, x, they stand as they are. So our KSP in this case is just going to be 2x to the power 2 multiplied by x. So now, understand that your KSP has been given. So your goal is to find the value of x. So your KSP has been given to be 1.2 by 10 to the power negative 5. Being equivalent to what? 2x is going to be 4x squared multiplied by another x to the power 3. So divide by 4 and determine the cube root. So your cube root on the calculator is just below the on button. So shift, then you find the third root there, then put the figure down there. You find your solubility in this case. In a case where you're talking about the solid in water. Questions? So now, in the second solution, we already have silver nitrate dissolved in the solution where we are trying to dissolve the silver sulfate. So it's like, if you look at this silver nitrate, it has got a silver part of it, right? So that silver is going to affect the solubility of our solid in this case, meaning that we already have the initial concentration of the silver in the solution. So this concentration that we've been given, we are going to show it as the initial there, 0.1 for silver. Sulfate was not present in this silver nitrate, so it's 0. So we're going to have 2x plus 0.1, then the other side you have x there. So this is supposed to be raised to the power 2. Okay. So now, for this part, for only information, no need of you ignoring the addition. We don't need to ignore the addition. Why are we not ignoring? Because we want to see the difference between a case where we have water and a case where we have the silver nitrate. We get to see the difference in solubility that we're going to have. Are we together? So find the value of x there. So expand this, multiply by x, and equate it to what? And equate it to the given value of KSP there. Any questions? So now, by contradiction, or in the second part of the question, in the third part, where they've given you 0.2 molar concentration of potassium sulfate. Yes, yes, yes. So I was saying, just like we come up with any other K constant expression, even for KSP, although in most cases they give you a general question where they don't tell you where they're going to put it. So that is like the first part of where we're talking about water. We are saying in such a case, the initial is 0 for the ions. Now in this case, if you look at the second part where we've told you 0.10 molar concentration of silver nitrate. So you already have silver ions dissolved in the solution. So meaning that you are going to have an initial concentration of that instead of just it being 0. So you already add the ions present in the solution. And it has only applied to silver because only silver was present. So now I'm saying for the second part, we have potassium sulfate. So we've been given the its concentration as well to be 0.2. So now I'm saying now in this other case, instead of you adding your silver silver is going to be 0 there. Now your sulfate is going to have a concentration, an initial concentration. And you get to do the same. Okay? So here you have 2x. There you now have x plus 0.2. Then your goal again is to find the value of what? X by equating it to the value of the KSP that you've been given. That is what I was saying. Are we together? For water, there is not. We just answered it the way we answer questions under KSP expressions, where you just say, okay, just ignore everything. Like since you have 2x, you just say your KSP is 2x the power 2 and multiply by x, so that you have 4x squared multiplied by x, giving us 4x the power 3. Then you equate that to the value of KSP, which is 1.2 by 10 to the power negative 5. Then you find your value of x. That's what we did for water. Nothing changed. Just a normal approach, just like we answered question 11. No, there's nothing to do there. We don't have water. There's no concentration of the ions. We don't have the silver and the sulfate, so it won't affect the solubility. To just do the normal solving. There will be no initial concentrations. No initial in short, no initial concentrations for water. There are no silver and sulfate ions are not present in water. Because we are only showing, and I'll repeat, we are only showing the ions that are present in the solid of our interest, which is that one. So if the added salt or whatever solid you've added in the solution, as long as it is not adding silver and sulfate, it will not have any effect on the solubility, on its solubility. Yes. Yes. So have we understood the difference between the two cases, where you have the ions dissolved and where it is just water? Okay. So now, what is covered in your tests? May I know what is covered in the test? Chemical kinetics, equilibrium, and what? Acid base equilibrium, okay. Chemical equilibrium, corrugative properties. What else? So is there anything that you didn't understand? Or do you have questions that are still hanging on these topics? I think I left out a few questions from that story sheet under kinetics and also chemical equilibrium because I didn't talk about this part. So I'm sure there are some questions on this part and also the other part. So I can finish up the questions and I'll send you the solutions as soon as possible tomorrow. Then with chemistry, we are set. I don't know about math.